so that we can share. Excellent. Welcome everybody to our STEM workshop. This is the first public workshop that we are holding for the United Nations Development Programme within South Africa. And here we're looking at the Sustainable Development Goals. So what I'd like to do is that I'd like to introduce everybody who's supporting the workshop today. And what we've done is in the last number of months, there's a number of us who've been trained as educators to facilitate and deliver this program. And hopefully you'll be able to see them on the side panel. So we have Reno, we have Brittany. Brittany is really going to be helping me making sure that all the questions are attended to and answered. We have Nico, Colin, Denise, we have Becca, we have Banele, as well as in Tabaleng. And we also have Amina. And Amina has joined us from KwaZulu-Natal, and she is one of the students who was very successful on the Africa-wide STEM program relating to the Sustainable Development Goals. And she was actually, she won an award as being a great ambassador for Africa in terms of STEM and the Sustainable Development Goals. So Amina, thank you very much. I also believe that Amina is probably going to be able to answer a lot of the questions that I can't answer because her knowledge is a lot more up to date than mine is. So yeah, what I'd like to do is I'd like to quickly go through our agenda. So what are we going to be covering today? We're going to be having a look at, well, we're going to do some welcome and introductions. We're going to go through our first workshop, which is going to be looking at Sustainable Development Goal number 15, Life on Land. We'll have a break between 12 and 1. And what it is that we're going to send you a link to an assignment, Living on Antarctica. It's a quick quiz, which we'd like you to do during the break. Then we'll come back at 1 o'clock and we'll go through our second workshop, which is our Earth in Context. We're going to be having a look at our solar system and what happens, what is the impact of a solar eclipse when we, in terms of our Earth and the sun and the moon, etc., in context of our solar system. And then what we'll have is there's a final assignment that is due on Monday at 8 p.m. On the 16th of August. So without anything further, what I'd like to do is let's do some introductions. And what I'd like to do is I'd like to just introduce myself first. And then what we'll do is we'll go through our various panelists for them to introduce themselves and where they're calling in from. A number of them aren't going to be on video, but that's absolutely fine. From a housekeeping perspective, please go crazy on the chat. Have a wonderful time. However, if you do have a question that you would like me, Judy, or one of your panelists to answer, then please use the question and answer, the Q&A section, because then we'll be able to manage that a lot better. So yeah, okay, so an introduction. Let me introduce myself first. So my name is Judy Sandrock, and I am participating from Cape Town in the Western Cape. And I'm an engineer. I'm a chemical engineer, and I have been, I graduated last century. And so I worked as an engineer for many years. And so therefore my approach to STEM, science, technology, engineering, and maths, is I don't approach it as a teacher or as an educator. I actually approach it as an engineer. And everybody that I engage with, I engage as if they were budding engineers or engineers. So therefore, I'm not going to be treating you as a student. I'm going to be treating you as a fellow engineer during these workshops. And yeah, so what do I do nowadays? I still work as an engineer. I'm very busy assisting with the development of modular electronics. I assist a number of schools and students build, design, and build their satellites and put them into orbit. We run projects on the International Space Station. We run projects on Antarctica, which I'm going to discuss a little bit later. So that's a little bit about me. Let's actually go through. Reino, would you like to introduce yourself?
Yes, Judy. Let me just put my video on.
We can't really see you. We can't really see you. Let's just,
can you see me now?
Yeah, there we go.
Okay, good morning, everybody. I'm Reino Lefleur. I was fortunate to be selected a few weeks ago to form part of this amazing group and to have an amazing facilitator such as Judy. And she made everything so easy. Initially, I thought I would have struggled in terms of electronics and the engineering and the science part, especially linked to space, etc. But she and Brittany made it possible for myself, and I think all the rest of us that participated, so that we start to understand how these electronics and components merge together. But other than that, I have my own company, Access Tutoring, whereby I try to extend my knowledge in relation to the fourth industrial skills as much as possible, and therefore I applied for this program so that I can be able to extend my knowledge and then to take that same knowledge and filter it through to the various communities and schools that I'm already working at the moment. At the moment, I'm doing game-based coding, but this United Nations topics, of which all of you will be introduced today, is so relevant and so informative, related to our futuristic careers that we all head towards. So yeah, that's in a nutshell. This is a very informative session, program, and it can assist all of us, and all of these various topics can on one or the other way be filtered into the CAPS curriculum at our schools. And yeah, we all are linked and bounded to the Sustainable Development Goals, and this program basically cover most of it, or it enlightens your mind and view towards certain things, and you will definitely see it from a different angle after this program.
Great. Reino, thank you very much. Brittany, over to you.
Everyone, my name is Brittany Bull. I started as an intern at X in a Box, but before I was an intern at X in a Box, I myself was one of the students who was a beneficiary of this program when I was in high school. And I'm an engineering student. I'm one of the facilitators. I work closely with Judy and the rest of the teachers on this program. And I'm going to be answering a few of your questions today. And I'm also a self-taught software developer. And today I'm excited to be answering all of your questions and helping you on your learning journey in this program.
Fantastic, Brittany. Thank you very much. Brittany's also in Cape Town. She's just down the beach from me. And yes. Yeah, absolutely. So Amina, how about you? If you wouldn't mind introducing yourself.
Okay, hi, my name's Amina. I'm from KwaZulu-Natal, Mooi River, which is a really small town. I'm currently in high school. I'm in grade 10 and I go to Treverton College. As Judy said, I was on the STEM program with the whole of Africa, and it's been an amazing journey so far, and I've made amazing friends, and it's like been really good. And yeah, I'll try and answer questions if you guys have any with my knowledge from there. Thank you.
Fantastic, Amina. Thank you very, very much. And Nico, how about you? Where are you at the moment, Nico? You travel quite a lot.
Morning all. Thanks, Judy. Super excited to be part of this as a facilitator. I'm actually just down the road from Judy. I'm in Strand, Western Cape, so in close proximity. I come from an electronics engineering background, so I'm what they call the tinkerer and maker, you know, playing with circuit boards and all of that. I still do in my spare time, do a lot of projects with various boards and stuff. But I think for me, what makes me excited is to share my experience and my knowledge, because apart from the electronics background, my day job is as a project manager, and I've worked in various industries. So sharing actual real world experience, you know, with the group, that I would like to contribute. And then, you know, my passion for electronics, you know, sharing that knowledge and carrying it over to the group and to facilitate. And yeah, as I said, super excited to be part of this. Thanks.
Excellent. Wonderful. Colin, how about you?
Hi, thanks, Judy. Good morning, everybody. My name is Colin, based out in Blouberg in the Western Cape as well. Very excited to be part of the journey with Judy. I'm a proud alumni of her program, and I have to tell you, you are absolutely going to enjoy this. Personally, I am also a tinkerer or a maker, working a lot with hardware as well as software. So both those skills will certainly come into play. And I think what glues it all together is exposure to STEM. I know during school, a lot of kids ask the question, when will maths ever help me? You know, when will science ever help me? And I think those questions will be answered on this particular forum. So my role here as well is to provide you and the team with support. Yeah, any questions required, any assistance required, we're here to help. Thank you.
Great, Colin. Thank you so much. Denise, how about you?
Hi. Just waiting for my video to come on. Oh, I'm at the wrong place. Sorry.
Oh, don't worry. Don't worry. It's fine.
Oh, yes. Denise and Colleen is here. Yes.
Nice to see you guys.
We're from SEDIC in Douglas in the Northern Cape, very small town, rural. And we've got a maths and science center here, and we work with a lot of students and a lot of learners in the different schools. We also have a branch in Priskande, so we would like to extend this program to them as well. Yeah, my contribution, I would say I'm very involved with the ESCOM Expo as well. And we have already tried the X in a Box this year with grade 6 learners from Farless, which literally has only 2 classrooms, 2 teachers. The one classroom is from grade 1 to 3 and the other one from grade 4 to 6. And it's a very tiny, very rural school, and they had fun with it. And yeah, my contribution, I could help with answering questions about the scientific method and doing a whole scientific project. So yeah, I'm very excited to be here. Colleen, do you want to say something?
Well, I'm here in the learning capacity. I haven't got a lot of electronics or IT background, so I'm glad to connect and network, but well positioned to introduce this program to other learners. But I must say, Judy, for me, so far, being made aware of the Sustainable Development Goals from the United Nations was, for me, already new, and we've already done some progress with our team based on Think Global, Act Local, and discuss the Sustainable Development Goals with some of our team already. So just that part is already filtering through to our team, which has been exciting.
Fantastic. Thank you so much. And Becca, how about you? You're also in KwaZulu-Natal, hopefully a little bit warmer than we are.
I'm quite jealous after everybody has been saying they're from Cape Town and I'm just here in Durban. The warmest place, really, the warmest place in the entire world is really not the warmest place. Currently, it's so cold. It's so cold. My name is Bega Mbonambi. I'm a graduate. I'm a horticulture graduate at DUT. I'm a postgrad student tutor for the modules, and I'm learning. This is just, I think it's still my time to just learn as I develop and grow. So it's a fantastic opportunity, and I'm here to answer questions about plants physiology, plants development, and anything related to research in plants. I can be of assistance in that. So thank you very much. Let's just enjoy ourselves and have a learning experience. Thank you very much.
Wonderful, Becca. Thank you. Milena, how about you? You're in Gauteng, aren't you?
Yes, can you hear me?
Yes.
Good morning, everyone. I hope I have enough of my students online here, so I'm particularly greeting them. I was very happy to see some of them qualified for this workshop. I'm a teacher in a primary school, but I sent the link for this workshop to, or rather for the application to all the schools in my area. I'm in Germiston, and there are lots of schools from Germiston and Edenvale that received that link. I don't know how many of them applied and qualified. I only know my students from my school. I'm a teacher, science teacher, and I'm very, very passionate about enriching the children that have this innate curiosity for science. I'm very fortunate to know some of them in my school, and I want to keep them interested and to keep them enriching themselves, because at some point the young children have to try to find their own answers. We're here to facilitate their learning, to guide them and direct them, but they have to be finding their own answers. And that's why I'm very happy to be part of this project.
Fabulous, thank you so much. And yes, you have a background in meteorology. So if anybody has any questions about climate or weather, I'm sure Milena will be able to answer those. And also, I was thinking this morning, the Cape Town weather is so unpredictable that I think that some of the team from Cape Town will agree with me that sometimes it's not a meteorologist you need in Cape Town, but more like a psychologist. So yes, so I think let's begin our workshop, and let's see how we can share a lot of our knowledge. And there has been some reference to X in a box and modular electronics, and that is because what we're doing is that this particular program for the United Nations is that what we're doing is that we are using modular electronics to collect data. So it's very simple modular electronics that one connects. So what we're doing is we're using this modular electronics so that we can build scientific instruments, we can conduct our experiments, either collecting weather data, data about gases and light, different light frequencies. This is a particular kit that I would put on a high altitude balloon, and sometimes they're exactly the same kits that go onto rockets and into orbit or to the International Space Station. So today, because not everybody has a kit with them, we're going to be going through a lot of the data sets that have been collected by those kits, so we can actually see how we apply the data science, how we use data and mathematics to actually understand the world around us. What you will find is that at the end of today, you'll have a final assignment to submit based on what we've covered today. And that assignment is going to get you from this short list that you're currently on onto a final list. And what we're looking for is we're looking for those students who are actually very, very eager to participate, so that you can all receive your own kit at home and then participate in the workshops. So what I'd like to do is let's actually start. And I'd just like to repeat as well, please, if you have any questions, post those into the Q&A section. So let us have a look here. And so our first workshop that we're going to be looking at today is we're going to be having a look at Sustainable Development Goal number 15, which is life on land. And so the thing is, when we look at the Sustainable Development Goals, there are a lot of them. There's 17 goals. So let me actually go back to that graphic. You can see here there's 17 goals relating to how can we reduce poverty? How can we make sure we reduce hunger, etc. How can we make sure that life on land is comfortable and sustainable? Life below water is also comfortable and sustainable, etc. So the United Nations, all of the countries who are members of the United Nations came together a number of years ago and set these goals. And what we have is for each of our countries that belongs to the United Nations, we have certain goals that we're looking to achieve. So today we're going to be having a look at life on land. So let's actually get going with our first topic, which is comfort levels. So I think a number of you will have seen on the news and will have seen around the world that there's a huge challenge at the moment with temperature, high temperatures, especially in the Northern Hemisphere. There's been record high temperatures in Canada, for example. They've never known temperatures above 40 degrees centigrade, and they have been having those temperatures in their summer this year. And also we have a challenge with wildfires. So for example, in Canada, because their nature is just not used to such high temperatures, it's just one large tinderbox. They have fires again in California, and these massive widespread wildfires in California have now become an annual thing. This is not something where it's an exception, but certainly it's something that happens annually. And this is all related to our life on land, and it relates very much to this combination of temperature and relative humidity. So what I've done is that I've started off with this chart over here. And can everybody see this chart with relative humidity and temperature? Brittany, please let me know.
Yes, you can see the comfort levels and living habitats chart.
Absolutely. Fantastic. Thank you very much. Great. So let me just unpack this a little bit here. So what we have on our vertical axis is we have relative humidity represented as a percentage. And then what we have on our horizontal axis. Sorry. Can I go ahead?
Yes.
Okay.
Yes, you can.
Great, thanks. And then what we have is on our horizontal axis, what we have is temperature. And you can see here that it's actually represented in both centigrade and Fahrenheit. And that is because there are still some countries who have the imperial system, which is Fahrenheit. In South Africa, we use the metric system, degrees centigrade. So our freezing point of water would be 0 degrees centigrade, and our boiling point at sea level would be 100 degrees centigrade. So what we can see here is that during summer, as human beings, in fact, as any life on our planet, whether it is flora or fauna, what we prefer is during summer, we are comfortable at higher temperatures, which we would expect because it is summer. The temperatures are higher during summer. But the thing is, what we prefer is that it's not too humid, so it's not hot and sticky. We do prefer that it is slightly drier. And obviously what it is that above 27 degrees centigrade, we start getting very uncomfortable. And so the thing is that we don't like it to be drier than 19.8% relative humidity. And we certainly don't like the temperature to be higher than 27 degrees centigrade. The opposite is the case during winter. In winter, our systems, our biology has been set up that we are comfortable in winter with lower temperatures, as well as it being a little bit more humid. So as we can see here, we are still comfortable at 86.5% relative humidity. That's a big difference from 19.8%, which was the very extreme for summer. So the extreme for winter is we really don't mind if it's pretty humid, and we are okay with temperatures just below 20 degrees centigrade. Now, of course, this is representative of what we would require if we didn't have winter clothing on. So the thing is that the reason why we want to wear warm clothes in winter is we want to actually make sure that our bodies are at 19.5 degrees centigrade and higher. So we can see here that we actually, depending on the season, our comfort levels do vary slightly, but of course there's this wonderful green zone in the middle here where we are comfortable all year round. And so let's take this and then interpret it a little bit further, and let's have a look at what happens on Antarctica. So as South Africa, we are extremely lucky. We have a base on Antarctica called the Sinai base, and what it is that you will receive a link a little bit later to some very interesting articles, as well as a map which actually shows where that base is on Antarctica. And what we have is we have teams of engineers and scientists and meteorologists who go to Antarctica on a mission. Their total mission is around about 18 months because it takes a few months to get there and it takes a few months to get back. The boat always leaves Cape Town, the Agulhas. It's an icebreaker, and what it does is it leaves Cape Town late November, early December every year. By the time they get to Antarctica, it's during January sometime. They have a little bit of time with the team that they're taking over from, so that they can share knowledge, they can actually do a handover, and they can do a lot of skills transfer. And then the boat leaves again before the ice starts to reform on the coast. And so the boat leaves around about late February and then arrives back a few months later in Cape Town. So the total mission is around about 18 months. But what they do is that they usually spend just over a year actually on Antarctica. So what it is that they have a number of kits. They have another number of weather station kits on Antarctica. And this is data collected inside the habitat. So I'm not sure how many of you can see that what it is it actually says here that the data was collected between April the 3rd last year and July the 25th. So this was kind of like autumn to winter time. And so this is, and because we know that, we definitely know that this data was collected inside the habitat. Because if it had been outside, it would have been way below 0 degrees centigrade. And we have a temperature range here of anything between 10 degrees centigrade and maybe 17 or 20 degrees centigrade. So for inside conditions, that's actually fairly cold. So that means that one needs to have winter clothes on all the time inside the habitat. So we can see here temperature ranges between 10 and 17 degrees. But wow, look at this relative humidity. The relative humidity is between 10 and 20% relative humidity. So it's cold and it's dry. And the atmospheric pressure is relatively low. We would expect it to be around about 101 Pascal, 1,000 pascals, which would be atmospheric pressure. But the pressure is low, which is quite interesting, relatively low. But yeah, what we're really looking at here is we're looking at the relative humidity and we're looking at the temperature. And so what does that tell us? Let's go back to our other chart that we have over here, and we can see that that point on our graph of relative humidity between 10 and 20% and temperature between 10 and 17 degrees centigrade is way below and way off the comfort zone. So the conditions that the scientists and the engineers are living under is pretty uncomfortable for that year that they're on Antarctica. So let's just have a look at what other conditions are they being exposed to. So what we have here is, this is a graphic. It's not to scale, but what it does, it gives us a very good idea of our planet Earth. We can see here's our continent, Africa. And this graphic represents the magnetic field, our Earth's magnetic field. So we have our true north, which is our geographic North Pole, as well as our geographic South Pole. And you can see it's got this little arrow. And what this denotes is that this is the center of, this is the axis of rotation, which our planet actually rotates. And that is offset slightly from our magnetic North Pole and our magnetic South Pole. So what we're going to do is that we're going to open up for a number of questions. And so what I'd like to do is that I'd like to pose to everybody. And if you wouldn't mind, Brittany, if you wouldn't mind just typing a question into the Q&A. And then, you know, everybody can maybe have a look at answering that, is we have a magnetic field that is generated. And we can see these field lines here, these magnetic field lines. So can anybody guess, or does anybody know why we have this magnetic field and why it is generated? And why is it that our planet is fairly unique in having a magnetic field? The moon, I know it's not a planet in its own right, it's a satellite, but the moon doesn't have a magnetic field. Mars doesn't have a magnetic field. So what is it that makes our Earth, our planet, different, that we have a magnetic field protecting our planet? And so what we can see here is these field lines. And of course, on Antarctica, the field lines are extremely low because, of course, they converge at the geographic South Pole. And the same for the Arctic Circle. Those field lines are very low. And why is that important? Let's have a look at this slide. This is definitely not to scale. So please don't worry about us. Our sun is actually not that close. However, what this shows us is that this magnetic field in these pink lines over here, the magnetic field is actually protecting our Earth from a lot of solar flares, a lot of solar wind, which actually brings solar radiation. So not only does our sun emit light, natural light, but what it does is it also emits a lot of charged particles. Our sun is one large nuclear reactor. And so what it is it's a lot of actually really dangerous particles that are in our solar winds. And thank goodness for this magnetic field, because what it does is the magnetic field diverts these particles. So it protects us, except on the poles. What it is that some of the solar winds are actually able to reach the surface. So what it is that our team on Antarctica is fairly exposed to these very damaging particles. So they need to be very careful. They need to make sure that they don't spend too long outside without a lot of protective gear on. Even in summer, they still need to protect themselves from the solar winds. So what I'd like to do is I'd like to perhaps stop sharing now. I can see that there's a few hands up, and I'm sure that there's a number of questions. So Brittany, I see that you have your hand up.
Yes, I just wanted to draw your attention to a few answers that I got to the question that you posed about whether or not why Earth has its magnetic field. So the father in the Q&A answered and said it has electric currents in the liquid core. And then I saw that Amina Safla answered in the chat and said maybe because the Earth has a liquid outer core. And then Lerato in the chat also said, maybe from the cooling of the planet's interior when I was researching the Earth. That was the three answers I've seen so far.
Okay, great. Milena, I can see you also have your hand up. And sorry, you'll just need to unmute yourself.
Okay, it's the teacher in me that wants to always simplify it for the younger children. As far as I know, there are quite a few primary school children, and they're actually currently busy, the grade 6s and the grade 7s, doing electricity and electrical magnets. And they should know that electricity is in nature a flow of electrons, and it flows in metal. And what the Earth is essentially in the middle has tons and tons of liquid iron, which is a metal, and it flows, it circulates in the middle of the Earth. And that creates a very potent, very big and strong electrical current. And as the grade 7s are currently busy doing, they know that creates an electrical magnet. And that huge electrical magnet from the electricity creates the Earth's magnetic field. The older children that answered in the Q&A, they're high schoolers, they're more familiar with electricity. I'm just translating for the younger children.
Fantastic. Yes, absolutely. We're very lucky. We have a molten core, and there's a lot of iron in our core. The moon has a solid core. The moon has cooled over the millennia. It has a solid core, therefore it doesn't have a magnetic field because it doesn't have those electrons flowing as it spins. And exactly the same with Mars. Mars used to have a magnetic field because it used to have, billions of years ago, it used to have a molten core. And what it is that with all the probes that we've been able to send to Mars, drilling and understanding the surface of Mars and maybe drilling down a number of meters and bringing those cores back and analyzing those cores, we've realized that yes, certainly it used to have a molten core, and Mars used to have an atmosphere actually as thick as ours. But when its core solidified, that a flow of electrons stopped, and that field actually dissipated. And what happened was that if we were to imagine that this was Mars, what happened was that the solar wind actually blew away most of the atmosphere of Mars. So it's going to be very difficult for us to try to recreate an atmosphere on Mars because it's just going to get blown away by the solar flares. Excellent. Brittany, do we have any more questions or anything else?
Yes, Colin actually posed a question earlier saying, how will we achieve comfort levels when on Mars, which is, I think, similar to what we want to talk about today. I do want to get some answers in the Q&A from the students. I saw that Panela and Lerato were answering, and I just wanted to draw attention to that.
Excellent. Absolutely. Colin, would you like to come in and share some of your ideas?
Thanks, Judy. So is that a question in terms of the Mars element?
Yeah, in terms of how would we be comfortable in such an environment?
Absolutely. So I think, yeah, so for me, very closely monitoring what Elon Musk and SpaceX is doing in terms of looking at setting up a habitation on Mars. Quite clearly, based on the earlier graph that you shared, Judy, around our comfort levels, temperature and relative humidity becomes quite important, and we would need to find a way to artificially create those. The fact that the Mars is quite a distance away, how will we achieve it? So I do know that creating habitats that can create these artificial environments becomes quite important. Also, of course, as humans on Earth, we have oxygen in abundance currently. And the question is, how will we actually achieve that on Mars? I know that they have these huge, massive machines that have the capability of generating oxygen. I've forgotten the name of those machines, Judy, but essentially, we've tested the machines here. We make use of it in various other locations as well. So we would have the capability of generating it there. So certainly, that particular graph that you displayed earlier on gives us an idea, a good indication in terms of what do we need to do to ensure that we can comfortably, inhabit Mars ultimately.
Absolutely, yes, Colin, you are very, very correct. I think that if we were to look, if we were to look at how would we be able to survive in a particular environment. Oh, Becca, sorry, hi. Were you wanting to come in there?
No. Sorry, I'm having some difficulties.
That's great. Okay, great. Yeah, I think absolutely, and I think for everyone, if we want to have a look at how we would survive in a particular environment, what we'd need to do is we'd need to look at what resources are locally available. And one of the things we do know about Mars is that its atmosphere has quite a fair amount of methane, a fair amount of carbon dioxide. But also the thing is that in the areas which receive no sun, in shade, and also underground, there's actually a fair amount of water. And so if we were to consider, water has oxygen, H2O. And so what we could do is we could split the water using electrolysis. So what that would be is that is where you have two charged plates and you have with a huge potential difference between it. And what you do is as the current, you have an electrical current that moves between these two plates submerged in the water. And what that does is that it generates enough energy to break that very strong hydrogen-oxygen bond that we have. So what we have is we have oxygen coming off as a gas and we have hydrogen coming off as a gas. We need to put a lot of energy in to break those bonds, but it's a very well-known process, electrolysis. And in fact, not very far away from Becca and from Amina, south of Durban, there's a plant that does that for one of the food factories. And what it is that they needed a lot of hydrogen for making margarine, for converting oil, vegetable oil to margarine. And so a hydrogen plant was built there. And what they did is they used water and split the water into hydrogen. And then they had this wonderful oxygen stream, pure oxygen stream. And that was then used for augmenting the oxygen in the rivers. And also for other processes. So it uses a lot of electricity, And we would certainly be able to do that on Mars because we've got a lot of solar energy on Mars. So we'd be able to generate the electricity using solar power, and then we'd be able to find those ice reserves and then actually split that. So definitely we would be able to do that. And then the methane makes a very, 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 very nice fuel. So what we could do is we could use some of that oxygen, we could burn the methane for heat, because it's very, very, very cold on Mars. So any habitat that we have, we would actually have to heat that habitat. So maybe that's what we would do, is we would use the methane in the atmosphere as a fuel. Brittany, I see you have your hand up.
Hi, yes. An interesting question in the Q&A from Riza Kluter. He said, is it possible to take what we are learning from inhabiting Antarctica and Earth's magnetic field to replicate or apply this to living on other planets? And I think that's a really interesting question, because he's seeming to find the connection between what we are talking about to connecting it to living on other planets that's just as inhospitable, if not more, than Antarctica's climate.
Definitely we would do that. And a lot of the science and a lot of the research that is done on Antarctica is actually so that we can prepare ourselves for living in different environments. The one aspect is because we are exposed to so much solar radiation, we would be exposed to that in other environments on other planets. So how do we deal with that? How do we protect ourselves from that? Also, there's a matter of how would we grow food? So it's not only us as human beings who would need to be comfortable, we would need to have a sustainable living. So therefore we would need other creatures to be able to thrive and survive. We would also need to be able to grow food. So yeah, it's also about plants. We learn a lot on the International Space Station of how we would live in a habitat, because that is one environment where you can't open the windows. So if somebody is if somebody's cooking some really smelly food, they're very, very unpopular on the International Space Station, because you just cannot get rid of the smell. It's not one of those things. At least on Antarctica, you can open the window, but on the International Space Station, you can't. Colin, yes, you have your hand up.
Yeah, thanks, Judy. Just intrigued about your question around food. I think, yeah, for us on Earth, it seems something quite trivial and quite natural to expect. But of course, once we venture out, it becomes certainly an issue. I just wanted your comments on, there was a movie, I think it was Matt Damon in Mars, and famously known to go and grow potatoes. And, what are some of the vegetables do you think that potentially we could potentially look at growing on Mars? And I'm sure that a lot of learnings would have come out of what we've done on ISS.
Certainly, I think that Milena and Brittany will be able to make a contribution here in terms of that. What it is that there are a number of plants that are pretty successful growing in an artificial environment. Spinach is one, certainly tomatoes and chilies or capsicums grow very well in an artificial environment. So that's really where we would be starting. Colin, one of the huge challenges is actually the survival of the bacteria. The thing is that most bacteria is really, really, really good for us. And what we need is we need bacteria in our digestive tracts to help us digest food. So therefore, it's actually quite a lot of the time, it's how can we make sure that the bacteria survives in order for us to be able to survive. And what we've certainly found on the International Space Station is that bacteria relies quite heavily on gravity. So the thing is that in a weightless environment, a lot of the bacteria within our own bodies doesn't survive. And therefore the astronauts, they have huge challenges digesting their food. absorbing nutrients because they don't have enough of the right bacteria. And also, if you get an injury, a scratch, a wound, a cut, it takes incredibly long to heal. So these are a lot of considerations that we need to have in terms of living in habitats. Ultraviolet light is a really, really, really good disinfectant for viruses. And in a lot of these environments, in order to keep the atmosphere in, what we have is we have these panels which also then block the ultraviolet light. And so what we have is we have viruses really actually thrive in these environments where we are keeping the vacuum on the outside and the ultraviolet on the outside. So yeah, this is a huge topic. It's a very, very, very interesting topic, and it's certainly something that we can continue with. What I'd like us to do is I'd like us to start going into the break. So Milena, would you like to have your hand up? And then I'd like to hand over to Brittany to share the link for the quiz during the break.
Yes, 2 points very quickly. I know we are short of time. Tendai on the Q&A asked a very, very poignant question. Can we use water to drive cars? This is actually the future of fuel research, because being able to split the water into hydrogen and oxygen will allow us to have pure hydrogen fuel that is going to be a clean fuel and is going to be good for the environment. Unfortunately, people are just researching it at the moment, and at the moment splitting water into hydrogen and oxygen is much more energy consuming than it's effective. But that's where the future is going to die. And if you choose to be an engineer one day, hopefully we'll hear from you on that level. The other point is about Mars. To terraform a planet, or to terraform a small part of a planet, we need first water. Water is a non-negotiable, and we know that on Mars there are pockets of frozen water. It's been discovered already. So once we have those pockets of frozen water, we need to find a sustainable way to take energy to defreeze the water, to use it to plant. And what Matt Damon did on that movie was he isolated part of his place there, and he created favorable temperatures. And he used, there is lots of carbon dioxide on Mars. He used a little bit of defrosted water. And so when we have carbon dioxide, water and favorable temperatures, plants can grow. And that is why Mars is the one planet in the solar system that is ripe for terraforming, because it has all the resources we need. We don't need to bring water from the Earth. We don't need to bring any resources from Earth. We just need to discover how to use Mars's resources. Thank you.
I just want to add to what Milena said, and she's completely right. There is research from the Mars rovers, specifically the Perseverance rover, finding ice on Mars and harvesting that and making it liquid. So that wouldn't necessarily be an issue for us of the research and the experiments that we plan to do on Mars. We'd initially on the shuttle possibly have to take a certain amount of water for the trip, as we usually do for trips on Earth. We'd take some snacks with us as humans when we go on Mars and stuff like that, and then we'd refuel and get more things at our destination. So that's alternatively what it is. That's to answer Owami's question on how will we get water on Mars. And then Aiden and Ayub asked the question of won't it be too hot on Mars to plant plants and for them to grow? To my understanding, the plants would be grown inside the habitat, like the humans would live inside. So a good movie to watch on this, I know it is science fiction and it is a movie, but it has a lot of truth in it, is The Martian with Matt Damon, as Milena mentioned.
Brittany, thank you very much. Brittany, I hope you wouldn't mind I think I sent you a Slack message earlier with this link.
Yes.
If you wouldn't mind sharing that with everybody in the chat so that they can quickly go through that quiz during the break, because we're going to come back together again at 1. And then as an assignment, which would be due by 8 p.m. on Monday, this coming Monday, is we would like you to come up with 3 questions that you would like to ask the team on Antarctica. So what we're going to do is we're going to send you this link as well, but only at the end of today's session, so that you don't get distracted. But in that link, there's a very, very interesting article with a number of links with different videos and very, very interesting background to what it is like living on Antarctica. So we would like you to come up with 3 questions that you would have for the South African team living on Antarctica at the moment. We do have email communication with them. So what we would like to do is we would like to be able to send your questions to them so that they can actually respond to you directly. So that's what we would like to do. I would like us now to break and then come back together again at 1 o'clock to go through our second workshop. I do see that maybe there are some hands up and maybe there are some more questions. So what I'm going to do is I'm going to stop sharing the screen right now. And what I'm going to do is I'm also going to, that's great. So it's absolutely fine if you want to go away and then come back again at 1 o'clock for us to start again in just over 50 minutes. But Brittany, do we have any other questions that need to be answered or any other comments?
There are some questions in the Q&A, but we have answered a lot of them. Just to answer Karine, she just wanted to ask if we could elaborate on what you mean by there will be an artificial environment on Mars. I don't know if you want to elaborate, Judy.
Okay, that's great. Yes, what we would need to do is we would need to build a habitat, a sealed home, basically for ourselves and for anything else, any other life that we bring from Earth. Because the thing is that what we would need is we would need to develop an atmosphere that we could live in. Secondly, the atmospheric pressure on Mars is very low. It's roughly 1/10 of what we have on Earth. So what we would have to do is it would have to be a pressurized environment that we created. So that is what I mean by an artificial environment. We would have to create an artificial environment for ourselves to live in, because it would need to be pressurized, and also the atmosphere inside would have to be roughly 79% nitrogen, 20% oxygen, 1% argon and other trace gases, so that we could actually live and thrive ourselves, as well as any plants or animals that we were to bring with us. There's another reason why we have to have this sealed artificial environment. Is what we've got to be very, very, very careful of is we've got to be very careful of contamination of the Martian environment. We've been very bad as human beings, where what we've done is we've gone all over our planet and we've contaminated the environment that we have all over our planet, whether it is soil, whether it's water, whether it's air. We're very messy. And the thing is, we can't have a situation where we take viruses, germs, etc., into an environment on Mars. So everything that travels to Mars is built in clean rooms, is fully sanitized before it leaves. All of that kind of thing, so the thing is that up until now, we've been very, very, very careful what we've taken to the surface of Mars, so we don't contaminate Mars and contaminate the surface. When the astronauts came back from the moon, on every single one of those Apollo missions, when they came back from the moon, they had to have 2 weeks in quarantine to make sure that they weren't bringing anything back. Before they went, they had to be in quarantine so that they weren't taking any germs etc. Brittany, yes. Did I answer the question?
Yes, you did. Thank you. A Zoom user asked, sorry, another question. Would it be possible to restart, inverted commas, the water cycle on Mars due to the fact that even though we have found ice on Mars, would it eventually run out, right? So she's asking, unlike Earth, Mars doesn't have, I'm assuming, this is our question's thinking, I'm assuming that unlike Earth, Mars doesn't have its own magnetic field, and it doesn't have the sort of bubble, so to speak, that we have around Earth. How would the water cycle work on Mars?
Yeah, we can certainly see that when Mars had a much thicker atmosphere, when it did have a magnetic field and it was able to retain a much thicker atmosphere, there certainly was a water cycle, because we can see that there were rivers and lakes, etc. We can see the water erosion, evidence of water erosion on Mars. And of course, as Milena said, that we have found large pockets of ice underground and in shadows on the surface of Mars. What we need to take into consideration is, if we consider water itself, we have this phase diagram with pressure versus temperature for every substance. And so what we're going to find is, because the atmospheric pressure is very low, we're going to be below that triple point for water. So what we're going to find is that as soon as we start accessing that ice, we're going to have a sublimation situation, where what it's going to do is it's going to convert straight from the solid to a gaseous form. So we're going to have sublimation. We're not going to go through a water phase, because we don't have enough atmospheric pressure. So in order to recreate or restart a water cycle on Mars, we would have to start with creating a much thicker atmosphere. And that is a huge task. That is a huge task to do, because there's no magnetic field to retain that atmosphere. So if we were to restart a water cycle on Mars, it would have to be within a habitat, within a dome, within some kind of pressurized, in local, very, very localized environment. Brittany.
Oh, yes. Sorry. Risa Kluter asked, do you think that plants, when exposed to Mars environment over time, will evolve to something that adapts to Mars and would change their properties based in the comparison to what they are now?
Sure. That's a question for Becca. He's the guy who knows about plants. I know about chemicals. Becca, what do you think? What do you think? I mean, would plants be able to adapt to a much lower atmospheric pressure and a methane-rich environment? Becca, we can hear you. No, we can't, actually. Okay, I think Becca's having some communication problems. What we'll do is, why don't we come back to that question a little bit later? I can see, Lerato, you have your hand up. Hi, Lerato.
I wanted to ask if we are considering changing the radiation of Mars, since if it has intense radiation, how are we going to be able to change that?
Okay, Lerato, it's a really, really, really bad kind of signal. Yeah, all I can hear is that you're talking a little bit about radiation. If you wouldn't mind, could you type that into the Q&A, and then let's take it from there.
Okay.
Hi, Judy. We had another question from Aiden and Ayub in the Q&A box.
Great.
They asked, will the sun one day burn out and life on Earth would go extinct? I think that's a really interesting question. And I suggest, I don't know what your input will be on this, that they look at the research that SANSA does with solar weather and space weather.
Yes, absolutely. Yes, space weather is when we monitor the health of the sun, because it's a nuclear reaction. Yes, it will one day run out of fuel, but that's going to be billions and billions and billions of years from now. I actually reckon that probably life on Earth is going to have evolved to such an extent and may even have gone extinct before the sun burns out. So yeah, and there's also another thing is that with the expansion of the universe, and what's also happening is that because of centrifugal forces and centripetal forces, our solar system's actually expanding. So we are actually moving away from our sun. Our orbit is actually expanding at something like around about, they've measured something like 20 meters per year or something. I mean, it's absolutely tiny, but over the millennia, this does count. So we are actually moving further and further away from our sun. So yeah, it's just a matter of the Earth eventually will cool off based on how much solar radiation we receive. In the next session, we're going to actually have a look at how does our atmosphere actually convert that energy from the sun into heat. So that's why we're going to have a look at why do we have a situation with global warming when it should be getting cooler. So we're going to tackle that in a lot more detail than in the next section.
Yes, and then they had another question Lerato posed it earlier. So isn't heating water gonna affect the fish, since you said it's extremely cold? And how are we going to move animals to Mars? Are we going to take animals kind of two genders to have the process of reproduction happen on Mars? That's what Lerato is asking.
Yeah, it's going to have to be a little bit like an ark, like a Noah's Ark, 2 by 2. Certainly, yeah, I think that, one of each gender is probably not going to be enough, because what we need is a fairly large gene pool. So I guess that what we would need to do is we would need to make the decision up front, what species are we going to take, and then actually make sure that we have a large enough gene pool with that. What we could do is we could always, instead of actually taking the live animals themselves, we could take fertilized eggs or embryos. We could take that. We are able to cryogenically preserve. Cryogenics is the science of using liquid gases like liquid nitrogen to keep things extremely cold, like around about minus 190 degrees centigrade. What we have been able to do is we have been able to freeze, for example, fertilized fish eggs. We're able to freeze them, and then we're able to defrost them quite a bit later. Any trip to Mars is going to take at least 2 years. So what we're going to want to do is we're going to want to be able to freeze the embryos and take them there. When we talk about heating the water, yeah, I mean, we're going to make sure that we never heat it too much that it can't sustain life. So we're really going to be able to control that. I can see here, Brittany, there was a question about the quiz.
Yes.
Yeah, we've set up the quiz that sometimes you can select more than one answer. Other times there's only one correct answer. So yeah, I think that if you feel that there's 2 answers, you're going to have to pick. you're going to have to choose. Also, in the case where you can pick more than one answer, please don't just select all of them, because that doesn't mean anything. So yeah, what we're looking for is we're looking for the correct answers. So I hope that helps. Anything else that you think we need to address here? Karine, will the animals be able to adapt to life on Earth? Well, we've been adapting. Animals have been adapting for millions of years to life on Earth, so they're going to keep adapting. In fact, the human species, if you were to take the history of the Earth itself as a year, human beings have only been around for like the last 5 minutes of that year. So yeah, certainly everything is constantly adapting. So yeah, life is going to carry on. Human life may not be very comfortable, but everything else definitely certainly does adapt. Why can't we go further than Mars? Aidan and Ayub, we have gone a lot further than Mars. In 1974, as human beings, we launched Voyager 1 and Voyager 2, and Voyager 1 actually left the solar system a number of years ago. And the reason why we can say that it kind of left the solar system is because it was no longer impacted by the sun's gravity. So therefore it could be regarded as having left the solar system. So we can certainly go further. Right now, we're struggling to get back to the moon. So right now, the next target is Mars. The next destination is Mars, because we really, we're struggling to get life further. And the challenge with that is that if you have a spacecraft that only has to carry equipment, or electronics or mechanics or whatever it may be, you don't have to pressurize it. You don't have to worry about whether it's getting too hot or too cold or whatever. But as soon as you start taking life forms like ourselves, then you've got to have it pressurized. You've got to have enough oxygen. You've got to have enough water. It's got to be the right temperature, all of that kind of thing. It makes it a lot more difficult to put life on a spaceship rather than just sending probes. I hope that answers that question.
Yes, Judy, Karine made a correction, and she was saying she meant life on Mars. How would animals adapt to life on Mars? But you did answer that, I think.
Yeah, absolutely. I think that it's going to be the conditions on Mars, the natural conditions on Mars are so vastly different that it's very unlikely that any life that we were to take there would actually survive outside of a very controlled habitat environment. Viruses, unfortunately, may survive. But yeah, you know, the thing is that if there's no life on Mars right now, certainly our life that we have on Earth wouldn't be able to adapt to that environment. It's just too extreme.
I would want to pose the question. This isn't from the Q&A. It's a question arose from all of the questions about adaptation. Can you elaborate on how astronauts' bone density changes when they're in space? How will this affect other mammals that we might take to a place like Mars? I feel like that would be one of the first steps in adaptation for animals and humans on Mars in future generations.
Definitely, yes. Our bone density, what happens is that we're very, very reliant on having gravity as we know it. And certainly we've seen that muscle density and bone density does decrease when astronauts are on the International Space Station. And the reason for that is because they're there for extended periods. They'll be there for a number of months or weeks at least. And so there is certainly a deterioration, because the thing is, what we need to do is we need to be working against gravity. Another thing is as well is that our digestive system relies very much on gravity for our food to basically go into our stomachs. And so in a weightless environment, or when we're in an environment with a lot less gravity, we find we have digestion problems. And so that actually really affects the amount of calcium that we're able to take into our systems. So what we have is we have a net depletion of calcium from our bones. So therefore our bone density decreases, etc. Because then our calcium starts going into solution in our bloodstream. So yes, we are very, very reliant on having our atmosphere around us and having our regular 1G of gravity. So certainly that would be one of the adaptations that would take place in terms of assisting the astronauts when they're on the International Space Station, is doing kind of like weight bearing or load bearing exercise. That helps quite a lot. So they've got a lot of really very interesting gym setups there, machinery that they're able to use for exercise, so that it can actually create that that friction, etc., so that their muscles and their bones need to work, because they're not working against gravity on a constant basis.
And then one more question from anonymous attendee. Which case is more likely to happen first? The core of the Earth solidifying, the nuclear reactions in the sun stopping, or the expansion of the universe?
Okay, so in fact, all of those are actually ongoing processes. So the expansion of the universe has been happening ever since the Big Bang. So the expansion of the universe is ongoing. The sun is using up its fuel, and it has been using up its fuel ever since it became dense enough for the reaction to start. And the core of our Earth is cooling. It's gradually cooling, but I wouldn't know. I guess that would actually be a very good question for somebody like Neil deGrasse Tyson. I reckon he is somebody who would be able to answer a question like that. So yeah, maybe that's what we should do, is maybe we should tweet him that question and see what he comes back with.
Another question that Aiden and Ayub asked, can we create enough gravity on Mars so that we don't float away? How would they create gravity in the habitats, I think?
Okay, so gravity is a function of, if we consider the equation for gravity is, there's a gravitational constant, but the gravitational force, or the force of attraction of gravitational force, is a combination of, it's the product of the mass of the one body multiplied by the mass of the other body, divided by the square of the distance between them. So the closer you are to something, the larger the gravitational force. But a lot of that is, a lot in terms of gravity, is really dictated by the masses of the bodies. So in order to increase the gravity on Mars, one would actually need to increase the mass of Mars, which would be, I would say, pretty much an impossible task to undertake. If you want more gravity, you need to find a bigger planet. Yeah, I hope that answers the question. So no, theoretically, you should be able to increase the mass of a planet, but from a practical perspective, no, that's not going to be a thing. Brittany, should we take a break? and we half an hour.
Okay.
Excellent. Hi, everyone. I believe we're back from our break. And let's just see what I'd like to do is we have two more of the educators who've joined us for the session. Herman, you've joined us, and I was just wondering if you are online at the moment and if you'd like to introduce yourself. Okay, I think that maybe Herman isn't back from the break. That is absolutely great. Brittany, are you back with us?
Yes, I am back.
Absolutely, great. So I thought maybe what we should do is maybe we should get going again. Right, so let's just have a look here.
Hi, I am here.
How are you, Herman? Excellent. Would you like to introduce yourself?
Oh, okay. My name is Herman Maseko. I'm an experienced ICT trainer working for Saipono for 6 years, on which 6 years it was with the ICT department at Saipono in Newtown. So I'm stationed in one of the schools here in Joburg, east of Joburg, which is girls, the girls high school, Waverley Girls High School. I am working there as an ICT trainer. We have a solar lab there, so we training the learners, teachers, and community around there, especially the community of Alexander. So Alexander is just a, it's not far from Sentin. So 70% of the learners from Alexander, they are in our school there in Waverley. So that's why we are there, because of Alexander community. Most of them, they are underprivileged people from there. So that is why we are there. So another thing is that I had an opportunity of going around South Africa training what we call coding, and I am glad, and it is my actually pleasure to be one of the people who are in this opportunity that Judy UN has actually placed for us. Thank you very much.
Fantastic, Herman. Thank you so much. That's great. So, yeah, I think that we've been very busy with the Q&A section. So we have many participants, students who are participating in our webinar today, in our workshops today. And so, yeah, what I did is during the break, I just went through the Q&A, and hopefully I was able to answer most of the questions. So yes, please, if you have any questions or answers, please post them into the Q&A section. So what I would like to do now is I'd like us to go through our second workshop, which is our Earth in Context of the solar system, we're going to be looking in particular at a solar eclipse. And offline during the break, Milena and I had a bit of a discussion. And what we'd like to do is we'd like to actually have a little bit of a look at global warming and the greenhouse effect. So we're certainly going to be able to do that. And Milena, I'm going to be relying on you, please, to interpret me as an engineer for everybody else. So thank you very much for that offer to do that. So before we actually have a look at our solar eclipse, let's actually just go back to our Arctic regions a little bit. And what we're going to be doing is we're going to be having a look at what is a correlation. So a correlation is a mathematical term where we compare two sets of data. And what we do is we say, is there a strong correlation? Is there a weak correlation? Or is there perhaps no correlation at all? And this mathematical concept of a correlation is going to be absolutely crucial for you to be able to complete your next assignment, which is going to be based on analyzing the data from the solar eclipse. So let's have a look at these photos here that I found online. And yeah, what we can see is these are photos of polar bears. If we really look closely, every single one of these photos where there's a polar bear, there's some snow. So let's just compare that with some other photographs that I found with penguins. Okay, so here are photos of penguins, and we wouldn't necessarily say that every single one of these photographs of penguins also had snow. Hi, sorry. Sorry, was there a question? Okay, let me continue.
No, that was my mistake. I'm sorry.
No. Okay, no, that's absolutely great. Okay, so what we have here is we have penguins and what looks like grass. Penguins, this, I don't know, is this beach sand? Probably beach sand. I'm not sure if that's snow. This could probably be snow. I'm not sure here, bottom right-hand corner, is this snow or was this also just sand? Some rocks here in this middle at the bottom. In the background on those mountains, it looks like there's some snow. And this one bottom left, we have absolutely no idea if that's beach sand, nice white beach sand, or if it's snow. So we certainly can't say that there is a strong correlation between penguins and snow, whereas we could definitely say that there was a strong correlation between having polar bears and snow. So let's now have a look at a table here. And so if we were to convert this to a data table, we could say, okay, what we have here in our first set of photos, we had polar bears. Yes, there were polar bears in each of those photos. There was snow in each of those photos. So what we could do is we could have six of one and 6 of the other. So therefore we have a direct correlation. Our correlation is exactly 1 because it's 6 divided by 6. So here we can say that our correlation is firmly a correlation of 1. So in every single case where there was a polar bear, there was definitely snow. If we have a look at the photos with the penguins, we can't necessarily say the same because yes, we had 6 photos. You know, was there ice or snow there? No, maybe, no, perhaps half and half, yes, maybe, whatever it may be. But the thing is that there is definitely no correlation there. So what we say is we say that there's 0 correlation between there being penguins and snow or ice. And but then again, if we were to go back to those photos, in not a single case did we find polar bears and penguins in the same photo. The only time you find polar bears and penguins in the same photo or in the same environment would be in a zoo, and certainly not in nature. And is there anybody who can share with us why that is? Brittany, can you take over from me here? And actually, let's put that as a question to the group. Why would we never find polar bears and penguins in the same natural environment?
I'm waiting to see some action in the Q&A and chat boxes.
Great. Wonderful.
Ivan said, could it be that polar bears are predator and penguin are prey?
No, not necessarily, because then the polar bears would be eating the penguins. So no, that is not the reason why we don't find them together in nature.
Aiden and Ayub had the same conclusion as I when they said in the Q&A, would the polar bear eat the penguin?
Okay, so there's a clue. They're called polar bears. Where is the polar circle? In the northern hemisphere. And where do we find penguins? So there's a bit of a hint for you.
Tia Singh said penguins live in the South Pole and polar bears live in the North. And then Ashlyn said that maybe polar bears need a lower temperature. The father said polar bears live near the Arctic Circle, and Larata said maybe it's because of the temperature change.
Okay, so for those of you who said polar bears live in the Northern Hemisphere and in nature, and penguins live in the Southern Hemisphere in nature, that is actually correct. That they actually live in completely different hemispheres. So that is why they don't bump into each other in nature. And that is also why polar bears don't eat penguins in nature, is because they live in completely different hemispheres. So let's actually go back then to our table. And then what we can see here is in every single case where we have polar bears, we certainly don't have penguins. So here we can say that there is an inverse relationship. And so here the relationship, the correlation is -1. So in a case where you have two sets of data, if the one is a positive, and when the one is a positive, the other one is always a negative, then what you're going to find is you're going to find that the correlation is then calculated as -1. So this is very important when you get to doing your assignment. When you have a very positive correlation, it is +1. When you have an inverse or a negative correlation, it's -1. And if there's no correlation at all, in other words, there's no relationship between the two data sets, then it is 0. Okay, great. So Brittany, do you want me to pause a little bit for us to tackle some questions? Or should I continue going through our solar eclipse?
You can continue. There haven't been any questions other than answers to the question posed.
Fantastic. Okay, great. Are you able to see the solar eclipse slide?
Yes, we are.
Excellent. Okay, great. So on the 25th of August, 2017, so almost 4 years ago, there was a total solar eclipse that appeared on land. And it's actually relatively it's relatively unusual for a solar eclipse to be present on land, because the thing is that 70% of our Earth's surface is actually water, is ocean. So there was actually a solar eclipse, a total solar eclipse that appeared on land, and that was continental United States. And it was the first solar eclipse visible in the continental United States in 38 years. So of course there was a lot of excitement around that. There were a lot of people who were preparing for it, traveling to go to the right areas so that they could actually see the solar eclipse. And The position of the solar eclipse is also actually very important, because a part of your assignment is going to be to have a look at the data, to have a look at the time that the data was collected, and by doing a Google search of that particular solar eclipse, I'm going to want you to come back and tell us where exactly that data was collected. So the position of that solar eclipse is actually very important for you to remember as part of your assignment. So if we have a look at the mechanics of it, this is definitely not to scale. So what we have is we have the sun and we have our moon. As we know, our moon is in orbit around our Earth, our planet. Both of us, our planet Earth, as well as our orbiting moon, our orbiting natural satellites, we also in turn orbit the sun. And every now and then the mechanics work that what happens is that the moon casts a shadow on the Earth. And what it is it's regarded as, there's two zones of the shadow. There's the umbra and there's the penumbra. So the umbra is when it's a full shadow, and then the penumbra is when it's a partial shadow. And so this zone that we can see across the map of the United States of the penumbra would have been where they saw a partial eclipse of the sun. So there was only a partial shadow, and then there was a very narrow strip where they could see where there was a full shadow, and where the moon itself was completely concealing the sun from the people who were actually watching that eclipse. So it says over here not to scale, but let's just understand that. If drawn to scale, the moon would be 30 Earth diameters away from Earth. The sun would be 400 times that distance. Okay, so our moon is, yes, 30 Earth diameters away, and the sun would be 400 times that distance. So that is why this is definitely not to scale. Okay, so what we have is we have the light coming from the sun, and you know, if we take it from, let's say, if we were to take it from the top of the image of the sun, and how it casts that shadow, as well as from the bottom. Therefore, we have a partial shadow and we have a full shadow. So how does that actually interpret? So this was a photograph that was actually taken from the site where that data was collected. And here we can see this is a photograph of the eclipse. It was at the point where the eclipse was just about to end. So we can see the sun peeking around there in the top right-hand corner. But during a full eclipse, the moon conceals the sun. And so what we can see is we can actually see these solar flares, we can see the aurora. That is pretty important, because the thing is that what you will see in your assignment is there is a link to an article that was written about Albert Einstein. What Albert Einstein did is he theorized that gravity curves space, but he had no way of proving it. So what it was is that an experiment was then drawn up, and they felt that what they could do is, if they could identify a time and a place of a total solar eclipse, they would be able to see if there was something that was meant to be relatively behind the sun, would we actually be able to see it during the eclipse? I'm explaining this extremely badly, but please read the article, go through the video clip, and then you'll see that hunting down a solar eclipse was absolutely crucial for Einstein to be able to prove his theory. And that was because they took photographs during a total eclipse, and they were able to then measure what was happening with the light rays during that eclipse. So what actually happened on that day when the data was collected? So here we can see, here are some graphs that have been drawn from data that was collected during that solar eclipse. So what I'm going to do now is I'm actually going to grab a kit of mine and I'm going to stop sharing and I'm going to show you my little kit that I have here next to me. Yes, okay, I think this one will do. Let's just make sure that you can all see me. Brittany, I see you have your hand up.
Yes, when you done showing the kit, there's at least one very interesting question about the solar eclipse.
Okay, great. Okay, so what I'm going to do is that I'm going to show you a kit. Here is a kit. This is a typical X in a box kit with this modular electronics. And so what was used on that particular day was the weather sensor. This little guy over here, this little chap over there was used to collect data relating to temperature, atmospheric temperature, air temperature, relative humidity, as well as atmospheric pressure. And then also what they've done is they've added a light sensor. So the light, I don't have a light sensor with this kit, but it would be a similar looking sensor. And that would be looking at ultraviolet light, as well as natural light measured in lux.
We don't see you. We don't see you on the screen.
Are you not seeing my video?
Judy, I can see you. You should possibly pin yourself so that when somebody else talks, it doesn't switch to them.
Okay, so I'm pinning myself. Milena, can you see me now?
No, I see Colin Mamdo. I see his name.
Okay, in the top right-hand corner where you go to view,
okay.
Are you able to say speaker view?
Yes, it is speaker view and it says Colin Mamdo.
Okay, maybe just switch to gallery and then back to speaker.
Okay.
Let's see if that works for you.
Yeah, okay.
Okay.
Thank you.
Okay, great. Thank you. Because now at least for everybody, we all know how to do that. So yes, so the data that was collected was atmospheric air temperature, atmospheric pressure, relative humidity of the air in the area, as well as the light in lux level, because that's how we measure light, is in lux, as well as ultraviolet. But if we go back to those graphs of the data that was collected, we will see here that during the period of the eclipse, so we can see if this top left-hand graph, this is lux, so this is the light level, it dropped from over 3,000 lux to 0. It actually got pretty dark during that time of the total eclipse, and then you can see here that it started to recover. The data collection actually stopped there because the battery ran out, but that was okay. At least we have the data of it going into the eclipse. So we can see it was getting darker and darker and darker until it was almost completely dark. Very far top right-hand corner, you'll see here, it says unit number 2. Because interestingly, what it was is that they actually had 3 different weather stations collecting the data. The other 2 weather stations, number 1 and number 3, it got so dark that the lights in the schoolyard actually turned on. And so what that did is that interfered with the data. But unit number 2 was far enough away that it wasn't impacted by the lights actually automatically going on. That's how dark it got. We can see here that over the same time period, relative humidity as a percentage has increased. Bottom right-hand corner over here, we can see the temperature is definitely decreasing during that period and then starting to recover, as well as our atmospheric pressure was also decreasing during that period. So the exercise that you're going to do is that for all of you who have completed the quiz for workshop 1, we will have your email addresses from that completion. What we will be doing is we will be sending you the Excel spreadsheet, the data set here, and we would like you to calculate some correlations and give us some feedback on, are there direct correlations between these data sets? Is it a direct correlation? Is it an inverse correlation? Or there may be absolutely no correlation at all. So Brittany, let's actually stop here because you did mention that there was a very interesting question.
Yes, so Riza Kluter asked, just wondering if a solar eclipse has any sort of energy that can be harvested similar to solar panels harvesting energy from the sun. That was prompted by your slide earlier. I just thought that we could touch on how a solar eclipse affects solar energy.
Okay, great. In terms of harvesting the energy, because it's a solar eclipse and that part of our planet is actually in shadow, let's actually go back to that. I'm going to actually go back to that slide. Because we're actually experiencing a shadow, then what we're going to find is that we're not going to be able to harvest much solar energy because we're going to be in the shade. So that is not the energy that we would be able to harvest. What does happen though, is we can see here that we actually, and please remember, this is definitely not to scale. But what we can see here is that we have got a certain level of alignment in terms of the Earth, the Moon, the Sun. So from a gravity perspective, because gravity is a vector force. So the thing is that what we do find is that during periods of total eclipse, is that we do have abnormally high and low tides. And what was actually very interesting was that what we noticed actually around exactly that time, 21st, 22nd, 23rd of August, is that we had abnormally high tides in Cape Town. And so there were a number of areas that were flooded that usually don't get flooded by tidal effects. I only noticed this at the time because I happened to live in Cape Town. But that's what does happen, is that we actually have, it's the gravity impact. And harvesting that, the only way we can really harvest gravitational forces at the moment is actually through tidal power, through wind, by wave power generation or tidal power generation. So I guess that maybe we would be able to harvest energy from the eclipse in that way. Brittany, I hope that answers the question.
Yes, I think it does. Thank you, Judy.
Excellent. So let's actually just have a look here. Is what is actually happening here when we've got light coming from our sun? Okay, once again, this is not to scale. Light is the intensity of the light is inversely proportional to the square of the distance from the light source. Wow, that was like one hell of a sentence. I'm so sorry for that. But let me actually just unpack that. So if we had, let's imagine that this was a light bulb rather than the sun, and we were standing 1 meter away from that light bulb. And we had a sheet of paper that was, let's say, 1 meter by 1 meter, very large sheet of paper. What we would find is that there would be that light that we were getting from that light source would be covering that area with a particular intensity. So let's, just for convenience, refer to that as a light intensity of 1. Then if we were to move another meter away from that light source, so now let's say we increase our distance from that light bulb to 2 meters. Now what happens is that the same amount of light rays has to cover 2 times 2, which is actually 4 square meters of area from the same amount of light. So therefore we say that the light intensity is now a quarter, because it's 1 unit now divided by 4 square meters. So now it's a quarter of what it was before. And then if we were to move another meter away, now we can see if we're 3 meters away from our light source, that same amount of light has to cover 9 square meters. So now that intensity is only a 1/9. So this also explains why, if we were to go back to our solar system, what we'll find is that the further away we are from the sun, the lower the intensity of the sunlight. So those planets that are further away from the sun in our solar system, so they're further out in the solar system, they're going to get a lot less energy from the sun, a lot less sunlight. They're going to probably be darker. Well, actually, they will be darker. And also they're going to be a lot colder because they don't have any of that, of the heating from the sun. So this is just, it's quite interesting just to have a look at in terms of light intensity and how that dramatically decreases over distance. So now let's actually look at sunlight. So sunlight is very, very different, or natural light is very different from artificial light. So with artificial light, what we're getting is we're getting a very narrow band just of white light, which is a combination of all of the visible light wavelengths. And the thing is, if we have a look at this chart that we have over here, the sunlight has ultraviolet. The wavelengths include ultraviolet on the one extreme, and then also infrared light on the other extreme. So this chart over here on the left-hand side is showing us that actually the wavelength is inverse to the frequency, but the very, very high energy light is ultraviolet light. And what it is that UVA, ultraviolet A, which is a relatively long wavelength, it's more energetic. It has more energy than normal visible light that we can see with our eyes, because we can't actually detect, as human beings, we can't detect ultraviolet light. And then even more energetic is ultraviolet B. And then actually the highest energy is ultraviolet C. And that is actually why ultraviolet is so harmful for us, is because first of all, we can't see it, so we don't know we're being exposed to it. And secondly, what it does is it's very high energy, so it's very damaging to our skin cells basically our cells as a whole. And that is why when people say don't look directly at the sun, what it is that if you look directly at the sun, the ultraviolet light is going to damage the cells in your eyes. And so therefore, you could actually go blind, or you could really damage your eyes by looking at the sun too much. So this just shows us that the light that we can see, which is the visible wavelengths, it's denoted here by the colors of the rainbow, that is an energy band where we have ultraviolet is much higher energy, and then infrared is actually lower energy light. And what we're going to see is that infrared is often associated with heat. So, and that is why, and let's actually pose that as a question. When would we want to use infrared to detect what? When would monitoring of infrared light be helpful for us? Let's pose that as a question. Okay, so I'm looking here at the questions, and I can see here that Lerat was asking a question here. Lerato, I think just in future, perhaps don't use the enter button, because every time you do that, it posts it as a separate question, because it looks to me as if this would actually, you would probably prefer this to be one question. Okay, why do we get radiation from the eclipse? Looking at the eclipse. So yes, Lerato, what it is that if you're looking at the eclipse when it's in totality, in other words, if you are standing in a position where you're in full shadow, it's not going to be particularly harmful. But other times during the eclipse, when you're looking at the eclipse, what you're doing is you're actually looking at the sun. And so what it is that you're going to be looking directly into that source of ultraviolet light, which is going to be unbelievably damaging for you. So I hope that certainly answers your question. And Reza is saying maybe in detecting heat or maybe movement when it comes to infrared. Definitely. Reza, you're absolutely right. Yes, Brittany.
So Farah was saying detecting outside body temperature, skin versus the inner body temperature, or to heat food. And then Joanne Dippenaar said measuring different distance. And Baker said detect wildfires.
Yes, absolutely. So whenever we want to when we want to detect heat, or temperature, we would certainly use infrared. It's a very, very good indication. Infrared is a very good indication of the heat, the temperature of an object. So yes, night vision goggles used in conservation certainly are where what we would be doing is we would be using the infrared light or the infrared shadow or footprint of an animal or a human, etc., to be able to identify, is it a buffalo, is it a rhino, is it a human, is it a jackal, whatever it may be. Definitely would we be able to do that. If we were to have cameras, let's say on satellites, and we were observing our Earth, we would definitely be able to observe wildfires and felt fires, because they would be giving off an infrared footprint. They would be saying, here I am, we've got a problem here in this particular area. So yes, our bodies, our skin, certainly what it does is that we do actually lose heat through our skin. And so therefore we actually are emitting small portions of infrared light. So that is certainly why what you would be looking for is to detect heat. That would be definitely infrared. Are there any more comments there, Brittany, or are there any other questions that perhaps we should consider before we move on?
Ashlyn asked, during a solar eclipse, is the temperature higher than usual?
No. And the temperature is going to drop because we're going to be in the shadow. It's a lot like if you walk from full sun into the shade of a tree, or maybe a sun porch or something like that, or an umbrella, it's cooler. So yeah, when you're in the shade, it's cooler. So it's not gonna heat up, it's gonna rather cool down.
And then a question to answer the question before. Katlego said they are used for remote controls, and Lerato asked, so is infrared capable of detecting movement?
Yes, definitely, definitely. As long as it's an object that is warmer than the environment. So it wouldn't be able to detect movement of something that was cold-blooded, like an insect.
Or some reptiles, right?
Yes, or some reptiles, absolutely. So it's not going to help you detect snakes or lizards or spiders. but it's definitely going to help you detect mammals, birds. So yeah, anything that emits, that is warmer than its environment, you'd certainly be able to detect. Colin, I can see you have your hand up.
Yeah, Judy, I just wanted to comment on the concept of infrared and where it's applied. A lot of us have security systems at home, and we have these little white boxes in the corner somewhere, and you see every time you walk past it, it goes red. And those are called passive infrared detectors, utilizing infrared to detect motion. Definitely,
absolutely, definitely. And also the thing is that infrared sensors are often used when we have spacecraft or when we have satellites from a guidance perspective, because the heat reflected from the Earth is going to be different from the heat reflected by the moon or by the sun. So just by using infrared sensors, we're actually able to determine where we are. Also, another thing is that now with the pandemic, whenever we go into a store, into a shop, you know, somebody either holds up a sensor to measure our temperature, or otherwise, I mean, I certainly know at our local Pick and Pay, as I walk in, there's a huge screen and it's detecting and it says what my temperature is, you know, how hot are you feeling today, Judy? And that is all done using infrared. Measuring our temperature using infrared. Great.
Just to add on the uses of infrared, like Colin and yourself mentioned, infrared sensing is also used in infrared image sensing. So taking pictures using an infrared camera on satellite technology. And some of the projects I've worked on at the university has been satellites that use infrared cameras to take pictures of Earth for agricultural purposes, but then also for remote sensing.
Definitely.
And then we had a question from Denise. Why does the humidity increase during the solar eclipse?
Okay. Denise, absolutely. So let's actually go back to those graphs so that we can all see what that relates to. Hang on a second. Okay, there we go. So what we're finding is that the temperature is coming down because we're going into a shadow. And yes, our relative humidity is increasing over here. So the thing is that if we take it to the extreme, where let's consider overnight, the air gets cooler and cooler and cooler and cooler, and then eventually we get to dew points. So the dew point is the point at which dew starts to form on the ground, on grass, on bushes, etc. And so what that is that's the point, that's the temperature at which we have a phase change from gaseous water to liquid water. So relative humidity is the amount of moisture, or in other words, the amount of gaseous water molecules that we have in the air. And the thing is that the warmer the air, the less moisture it can retain. Because the thing is that what it is, it converts from moisture droplets into gas, or basically steam, as we would commonly regard it as. So the thing is that what you are going to find is that more and more and more water droplets can actually condense to create that humidity, the lower the temperature. So if we take it to a complete extreme, if the temperature, if it gets so cold very, very quickly, that what happens is that it goes straight from, it becomes ice. That is when we get frost conditions, which of course nobody likes. So the thing is that what it is that the hot air, the warmer the air, the less moisture it can actually hold. So your relative humidity is going to be lower the higher the temperature. The relative humidity is going to be higher the lower the temperature. Colleen, am I explaining that properly? So sorry about this. Maybe somebody else wants to just explain it a little bit better. Okay, Denise, you have your hand up. Brittany, you had your hand up.
If Denise wants to go ahead first, she can.
Hi, no, she just wanted, it was actually Colleen that asked the question and she just wanted to give a thumbs up. Sorry.
That's great. Okay, that's fantastic. And yes, Colleen and Denise, you will find in the Northern Cape, in very dry areas, you will probably get frost if it's very, very, very cold, because the moisture will go straight to being ice rather than going through that phase of being dew. Definitely, because you're in a very dry area.
And then Liam asked, what is the effect of a solar eclipse on the Earth's magnetic field?
Okay, Liam, it won't affect the magnetic field. And the reason for that is the magnetic field is being generated by the electrons in our liquid iron core spinning. And so the position of the moon relative to the sun and our Earth is not going to impact that mechanism of the generation of the magnetic field from the electric current. It's a completely different mechanism. So yeah, we're safe, we're okay. We still have our magnetic field as we normally would during an eclipse.
And then Tofado wanted to know, is there a difference between solar and lunar eclipses that's not the alignment of the sun, earth, and moon? Are there any differences in a solar and lunar eclipse besides the alignment?
Okay, so yeah, in terms from a terminology perspective, a solar eclipse is when the moon moves between us on Earth and our sun. So what it does is it eclipses the sun. In other words, it hides the sun. A lunar eclipse is when on Earth we actually cast a shadow on the moon. So where we would normally, let's say, be seeing a full moon, and then the Earth moves between the sun and the moon, then it casts a shadow on the moon. So then the moon seems to disappear for a while and then come back again. But it's all related to exactly the same mechanics of how we orbit the sun. It's all exactly the same mechanics. There's no other reason for those eclipses apart from just the simple mechanics of our orbits.
And we had another question. Then I wanted some elaboration on why we have high waves and tides during a solar eclipse.
Okay, so what we have, I'm going to go back to this mechanism here. Okay, so once again, please remember that this is definitely not to scale. Okay, so the tides are created because of gravity. Okay, so 70% of our Earth's surface is actually covered by water, and which of course has mass in itself. And so the thing is that it's the orbit, it's the the orbit of our moon around our planet Earth that that actually creates the tides. And so so what it is it's the moon's gravity pulling on the water that creates a rise in the water levels. And then let's say, for example, when the moon is on the other side of the planet from that particular water body, then it'll be able to drop down again. So the moon's gravity is responsible for why we have tides, high and low tides. The thing is that to a very, very, very small extent, those tides are also affected by the gravity of the sun. The sun is, of course, a much more massive body than the moon is, but then again, it's a lot further away. So, so the thing is that there's a small portion of the tidal force that we have is from the sun's gravity. So when you have alignment here of sun, moon, and earth, there would be some impact because those vectors would be aligned as opposed to opposing each other. I think I would have to answer that in a lot more depth. I probably need to have a couple more pictures to be able to explain that. But it's about how gravity, it's the gravity of the different bodies that that produce the tides, and also in terms of the direction.
Hi, Georgie, I have my hand up. Can I just interject here?
Please, please do.
All right, so here how it goes. Imagine Earth is a bow, and you have one big giant next to that bow, and in between the Earth and the big giant, you have a smaller person. And the big giant is the sun, and the smaller person is the moon. When they're in the same line together with the Earth and they start pulling towards the Earth, both the pull of the sun or the big giant and the pull of the moon, the smaller person add together and they pull harder onto the bow. And when they pull harder onto the Earth's surface, we actually can feel that pull even on the ground, but the ground is not able to move. What is able to move is the oceans that are facing the moon and the sun in the same direction, and the level of those oceans rises. We call that spring tide. We actually have a name for that, spring tide. And it happens twice in a month. It happens when we have full moon, when we have the moon and the sun in the opposite sides of the Earth, and when we have a new moon, when we have the moon and the sun at the same side of the Earth on the same line. And in the rare occasions when we have sun eclipse, when the moon is completely covering the sun, then we have even stronger hold of the spring tide. Then if the moon is in first quarter and third quarter, 90 degrees from the direction of the sun, then imagine that bow. Just close your eyes and imagine that bow. We have the giant pulling it in one direction, the little person pulling it in perpendicular direction. The effect of the gravity kind of kills each other from the sun and from the moon. So the tide is very small. We call that nip tide. But what Georgie was explaining now with more scientific terms was that when the gravity of the sun adds up to the gravity of the moon in the same direction, that pull becomes bigger and bigger, so the tide becomes higher and higher. In simple terms. Sorry, Judy. Okay, I'm done.
That was a fantastic explanation. Thank you very much. Yes. Yeah, I think we need to put together some kind of a graphic for that. I really like that idea, as you say, that pulling in the same direction, and the earth is the solid land isn't going to move, but the water is going to be able to move. So that's why we have the tides. Thank you. Thank you. That was really a terrific explanation. How are we doing, Brittany? I want to be able to go on to our last slide.
Yes, we can go on to the last slide. There's a bit of just a discussion about how the solar eclipse affects the behavior of animals, especially nocturnal ones. And then Liam had one more question. What does the Ring of Fire solar eclipse mean in astrology? But I will answer that in the chat.
Okay, yeah. Astrology is an art, it's not a science. Astronomy is the science. So yeah, I'm so sorry, I'm a scientist. I won't be able to answer that one. Yes, and certainly nocturnal animals are very, very disturbed during an eclipse because it gets very dark and they're not expecting it. So yeah, the nocturnal animals are very unsettled under those circumstances. So what I'd like to do is I'd like to go back to natural light from the sun and also this whole aspect of infrared. So this is, of course, again, not to scale, please. So what we have here is we have our sun and we have our rays, incoming solar radiation from the sun coming through our atmosphere. And what happens is that with our infrared wavelength, which is relates to our heat wavelength from the sun, what happens is that as the sun's rays come through the atmosphere, a lot of the heat from that infrared is absorbed by the atmosphere. Now, oxygen and nitrogen, most of our by far most of our atmosphere is made up by oxygen and nitrogen. They are not very good at retaining heat. But what is very, very good at retaining heat is carbon dioxide. And what is even much better at retaining heat is methane. And methane we get a lot from rotting vegetation. Yeah. And carbon dioxide, as we know, we get a lot from the combustion process. So any kind of fires, any kind of industrial process, a lot of carbon dioxide. And also we breathe out, as animals, we breathe out carbon dioxide. And so it's actually those what are known as greenhouse gases, the carbon dioxide and the methane, that is now absorbing that energy from that infrared. Okay. And then, of course, the light, all of those light wavelengths hit our planet. And it's quite okay unless we're in areas where we've got a lot of reflection. So in areas that are covered in snow, that are covered in very pale sand, like deserts, and in some cases, oceans as well, what happens is that they then reflect the light. And when the light gets reflected back out into space, we then have more absorption of the heat from that reflected infrared. So, so what we find here is that with the buildup of greenhouse gases in our atmosphere, not only is our atmosphere warming because we have the incoming light from the sun, infrared from the sun, but also when we have reflection going out, we also get double absorption. So what it is that even more of that heat gets absorbed. So we have this almost kind of like, we have this compounding effect of, it's not only about the energy we receive from the sun, it's also when we reflect the sun's energy, when the earth reflects the sun's energy, we're also getting more and more and more absorption. And as you can imagine, as the atmosphere heats up, you know, in relation to Colleen's question earlier, you know, it's as the air heats up, it gets drier because it can retain less and less and less moisture. And so therefore we get extended deserts, the deserts grow. So therefore we have surfaces that are paler, that are sun bleached, and they are reflecting more sun. So that is why it really gets worse and worse and worse. And Milena, I was hoping that maybe you wanted to come in here because you wanted to address this whole aspect of global warming and greenhouse gases.
No, let's leave it for later because it's simply explained is what you said, but it can be elaborated more on a later stage. Let's leave it for later.
Okay, absolutely.
Right. You have double absorption of the infrared light, and it's also the biggest culprit is the CO2 and the methane, but there is also gases called CFC. That's also culprits that come from industrial production. That was the reason why deodorants were banned, or rather certain substances in deodorants were banned, and now the deodorants we have now are much different because they don't have those components in them. Let's leave it for later.
Yes, absolutely. You're very right. We used to have these refrigerants that were very, very, very dangerous when they leaked CFCs. I think they were like carbon fluor, something. I can't remember exactly what the expanded is, but you're very
carbon, fluorine, and I also forgot the next.
Yes.
Okay, Google it.
Chlorofluorocarbon. Chlorofluorocarbons.
Chlorine. Yes, chlorine.
Yes, thank you very much. So it was chlorine, chlorine,
and carbon.
Absolutely. Thank you very much. Thank you very much for that. Definitely. And I think that, yes, let's actually put together a session where we go into that in a lot more detail, because there is a lot of very, very fascinating physics and chemistry that we could cover there. And so what it is let's just have a look at this, this second assignment. And then after that, Brittany, let's go back to more of the questions. But what I'd like you to do is, as I mentioned before, those of you who have completed the first quiz that we had during the break, you will receive a spreadsheet with this data that was used to draw these graphs, the data that was collected on that day, 21st of August, 2017. And what it is at the time that it relates to was the time of the day that it actually was at that point of collection, okay? So what I would like you to do is using a correlation functions, and it doesn't matter if you use Microsoft Excel, if you use Google Sheets, if you use any of the other tools where you have a spreadsheet and you use mathematical functions, I'd like you to calculate correlations. So calculate the correlations between the different parameters like lux, which is the light intensity and temperature and humidity, etc. And what I'm going to do is I'm going to send out with the data. I'll send out a link to that assignment. So I'd like you to do those calculations and then put in those answers for those different correlations. And then also I'd like you to just elaborate. What do these different correlations tell you about what's happening? We've had quite a nice discussion about as the temperature decreases, the relative humidity increases. But let's also have a look at, can you come up with any ideas around as the temperature decreases, why the pressure would decrease, etc. Okay, so in other words, just elaborate a little bit, have some thoughts around what do these correlations tell you. And then the third thing is using the date and time of the data collected in the spreadsheet and accessing the map of the solar eclipse. So if you Google it, you will definitely find maps of that particular solar eclipse. I would like you to tell me where the data was collected, latitude and longitude. I'm also quite happy if you look it up on a map and you say this was the nearest town or the nearest city, or this was the particular state in the United States where the data was collected. I would like you to be able to work out from a geography perspective where the data was collected. Okay. So with that, let's just go through a bit of a conclusion, and then we're going to go back to the questions. So what we have is our Antarctica questions, and the solar eclipse assignment are certainly due by 8 p.m. on Monday. What's going to happen is that Brittany is going to share with you the link for you to submit your questions. So I can see that I've already received some emails during the break with those questions. what I'd like you to do is that I'd actually like you to go to the links in the assignment that Brittany's going to send you now, and maybe even redraft your questions, because you're going to learn a lot from those different links, and you're probably going to come up with some really, really interesting questions. And then after the grading of those 2 assignments, the successful finalists will receive their own kit. You'll receive your own kit, and you'll be enrolled into the full-time program, STEM and Robotics program. So with that, I'm going to stop sharing, and let's open the floor for some more questions. Okay, so I'm seeing over here that Milena is answering 10 days a question. Why do we have high waves during a solar eclipse? Do we have any more questions? Or
just to touch on Liam's earlier question, sorry to interrupt you, Judy. The Ring of Fire is actually an astronomy phenomenon and not astrology. I think that was a typo. The Ring of Fire is the name for when the sun's rays creates a halo effect around the moon because of the distance from the moon's distance from the sun in relation to Earth. So it doesn't fully eclipse the moon because it's not far enough away. Fully eclipse the sun, it's not far enough away. So the sun's still like peeping out as a frame around the moon. That's what the Ring of Fire eclipse is.
Yes, definitely. Definitely, because our orbits are not perfectly circular. All orbits are elliptical. So sometimes during a solar eclipse, the moon may be actually closer to us or further away, depending on where it is in its, if it's perigee or apogee in terms of its eclipse, because eclipses, the ellipse of its orbit, because they're not circular, certainly. And that's when you do get the Ring of Fire, and that is when we can actually start seeing those solar flares and all of that kind of thing. So very, very useful from a scientific perspective to analyze the surface of our sun in that way.
Anonymous attendee has asked, sorry, but what is the difference between astronomy and astrology? I think this is a perfect question for Judy to answer.
Oh, wow. I'm not sure if I'm the right person for this. Okay. So apart from the spelling, okay. Okay. Astronomy is the science of studying astronomical objects. So basically, it's a very, very ancient word from the Greek. And what it is astra is actually star. And so the thing is that astronomy is the study of objects in space, whether they are stars, planets, moons, or satellites. It involves astronomical distances, that kind of thing, where we have a look at different orbits of different objects, etc. Astrology has its roots in very ancient belief systems, probably like pre-religion, pre-theology, and it all relates to
constellations, if I'm not mistaken.
Yeah. It would be kind of like what the different constellations would look like from the surface of the Earth, depending on where you were on the Earth. So, so for example, in the Southern Hemisphere, we see Sagittarius constellation in a particular way, and then there's some mythology that relates to that. So it's that is why it's more of an art rather than a science, because it's all around imagery and what it looks like and the pictures that we create by looking at the stars. not necessarily the science that we understand from it. I think that is really the difference. The one is an art and the other one is a science.
Sorry, Judy. Astrology is more about how the celestial bodies affect human life, human behavior. It's more speculative art, and it has no bearing in physics laws. Astronomy has bearing in physics laws. Astrology has bearings in mythology and art and social sciences, not physics.
Absolutely. Absolutely. Thank you very much. Karine is asking, will the links to the assignments be sent to us through our emails as well? Yes. Yes. So, Karine, I need to explain why I paused there. What it is that we had more bookings than people who are actually attending today. So we've had we have some no-shows. And so what we're going to be doing is, that is why we're going to be using the email addresses that are submitted with that first quiz that was shared during the break, the lunch break. We're going to be sending the assignments and the data set to those email addresses, not to everybody who booked, because not everybody who booked is attending. I hope that answers your question. So essentially it is yes.
Judy, just to interject there, some people were unable to log in as there was trouble with the link, Arifa noted, and then they were asking before we got to the end of the presentation if we could share the first quiz again.
Absolutely. Yes, okay. I'm very, very happy you do that. Did you share it in the chat?
Yes, I will share it again, the first one.
That's absolutely great. And then I think that, Brittany, I think I also sent you a link on Slack to the assignment. So
yes, I shared that link as well earlier. I will share it again.
Okay, so there's two links. The one is for the quiz that was during the break, and then the other one is for the submission of the questions for the team on Antarctica. Great. I can see here, Tende, do you consider age in the final selection? We are 12 years old in primary school, and the depth is very big for us, Nathan and Natalie. Essentially, this program was put together for high school learners, high school students, but we're not going to be ageist about it. If you still want to participate, if you're younger than that, we're not going to exclude you simply because of your age. However, what we are going to be doing is the United Nations, we needed to start somewhere with the program. So we've started with high school learners. What we are going to be doing is we are going to be expanding the program. So we are going to be expanding it so we have a program for students who are younger. But we're not going to be discriminating against you based on age. Let's just put it that way. We now have your details. So what we can do is we're going to be inviting you to many different programs, and we're going to be making many, many more different opportunities available to you.
Judy, Riza is asking what are the kits used for? He was wondering if they're going to be used for the topics we spoke about, like weather stations.
Okay, so the kit is going to be, yes, it's essentially a weather station. So we're going to be looking at a lot more in terms of the science that we do, in terms of the atmosphere around us, physics and science that we do regarding our atmosphere. And also what we're going to include is we're also going to include a soil moisture sensor, because we're going to be doing some experiments which involve growing plants, growing food indoors. And we need to understand soil moisture as part of that. So there's also going to be a soil moisture sensor included. So we'll be looking at that. And then another thing is in terms of robotics, robots work on if this, then that. So in other words, if I get this input, then I do make this movement, or I then have this output. So the kits are also going to include different outputs. So for example, something that could then control a servo. So maybe it could move a mechanic, it could move a robotic arm. So let's say, for example, I want to move a solar panel so that it maximizes the light to maximize solar power generation, something like that. So you would have the output, the electronics for that. Let's say, for example, you would also have another one that can control an electrical circuit. So maybe what it would be is the light levels have dropped too low, so therefore I want to turn a light on, so you'll have an output for that. Or maybe my soil moisture level is too low, so what I want to do is that I want to actually turn on a water pump, or a sprinkler system, something like that. So you've got an output for that, because that's how we're bringing in the robotics. What we'll be doing at a later stage in the program, closer towards the end of September, is we're going to be having a robotics hackathon. And so you're going to be using those components to actually design your project, your robotics project. Brittany, anything else?
Yes, Elska was asking, she's just a bit lost for the second assignment. She wants some elaboration on what should be done.
Okay, the second assignment. Okay, so what I'm going to do is I'm going to go back to that. Okay. Oh, sorry. Okay, so this is the second assignment is all about analyzing the data that was collected during the solar eclipse. So what we're going to be doing is we're going to be emailing you, if you've completed the quiz, the very first quiz that you received the link for today. Once you've submitted that, what it does is it sends through with that answer. It also sends to your email address. So to all of those email addresses, we're going to be sending the spreadsheet of all the data that was collected. And what we would like you to do is, using the correlation function in any spreadsheet tool that you were to use, it would have a correlation function. We'd like you to calculate the correlations between all the different data sets. What I'm recommending here as well is, if you want to know how to do something, Google it, ask the question. There will always be a short YouTube video. There'll always be some kind of a wizard or something like that to help you with that. And then what we would like you to do is, we'd like you to elaborate on what do these correlations actually tell you. What does it tell you about the laws of physics, that if the temperature is decreasing and the atmospheric pressure is also decreasing at the same time? What does that tell you? Brittany, I can see you have your hand up.
Yes, there seems to be a lot of confusion with the assignments that are due by 8 p.m. So the two links that I've shared recently in the chat, the first one was the link to the quiz that should have been done in the break. And then the second link is the Antarctica assignment link. And then the assignment 2 that you are mentioning is not a link that I've sent yet. It's a link that they will receive in the emails after we've concluded the session, correct?
Definitely. Absolutely.
Okay. I hope that clears that up for everyone, because there's been a lot of questions surrounding that.
Okay, great. Yes. Both the assignment regarding Antarctica, as well as the second assignment regarding the solar eclipse, they are both due by 8 p.m. on Monday evening. That's Monday the 16th, this coming Monday. What I will do is, when I email everybody the data sheet, I will reiterate all of that, the different assignments and as well as the deadline. So I will re-articulate that in the email. That's cool.
And then in terms of coding for the program, Lerato was asking, are we going to use MakeCode? To my understanding, for the kits, the weather stations do come pre-flashed. So in the beginning, there's going to be no coding. There will be room for coding further on into the program, like at the hackathon. And then because of the modular electronic system that X in a Box Tech uses, they can either code via block programming with like something like MakeCode, or they could code with something like Arduino or other languages, correct?
Absolutely correct. So what it is that the kit, when the kit arrives, this core over here is going to be pre-flashed with Arduino code. For Internet of Things, Arduino code is actually the best language. And so the thing is, we've pre-developed the code so that it's very much plug and play. So it'll come already with its Arduino code. If you like, you can actually use these same components for coding in Java, Python, Arduino. This code particularly not MakeCode. It's quite interesting because over the last few months, we've had very much a change of heart or a change of mind in terms of MakeCode. What has happened in the MakeCode environment is that MakeCode was originally developed by Microsoft to support the microbit. And the microbit was brought out by the Microbit Foundation in the UK. And Microbit have since, over the last 6 months, they've come out with a Microbit 2, which is the newer Microbit. It has a different core, a different CPU on it. And Microsoft hasn't responded in terms of updating MakeCode. And so Microsoft has stopped supporting MakeCode, unfortunately. So even though a lot of your modular electronics, you're able to code using MakeCode, unfortunately, all of the new sensors that we bring in are not supported by Microsoft. So because they've stopped developing in terms of MakeCode. So it's very limited what you can do. So the thing is, what we've decided to do is we've decided that we're going to rather focus on the languages like Arduino and Python and Java, C, C++, which are very much more standard industry languages. Also, the thing is that Python is the language of the future. Python is the language of IoT. So we're focusing a lot more on that. Herman, I can see you have your hand up.
Yeah, thank you. I think you've covered what I wanted to ask, but also when I went through the videos of X in a Box, I saw other people, they were using Scratch programming. I don't know whether is it allowed to use Scratch programming. Should we use it?
Absolutely. The X in a Box team doesn't support it, but you shouldn't need support on it. If you're fully up to date with Scratch, yeah, you should definitely be self-sufficient. Yeah, there won't be any surprises. Yeah.
Okay, thank you. Thank you.
Absolutely. Brittany, do we have any more questions or anything, or are we going to conclude and call it a day?
I think we can conclude and call it a day. There aren't any more questions that haven't been answered already. Okay. Oh, one more question. Abdul Qayyum asked, will we be learning coding in this course?
No. Sorry, that's a very blunt response. Not directly, absolutely not. For those people, for those students who are very interested in the coding aspect, what we'll do is we'll have breakaway groups, we'll have more sort of informal sessions to cover the coding, but this is not a coding course. What it is that our focus on this course is science, technology, engineering, and mathematics. And technology from the perspective of how do we apply technology, not necessarily coding. And we're focusing very much more on the sustainable development goals, developing and running projects that relate to the sustainable development goals. So if you're very, very interested in coding, there's plenty of coding courses that are available. Brittany, I mean, you've yourself coding. You didn't need Judy to teach you coding. I'm also the wrong generation to teach coding, to be very blunt about it.
I'd be happy to share some resources once we get into the course deeper for anybody who would like to learn and need more support. And then just to reiterate for the times that the things are due, Monday 8 p.m. for everything, correct?
Yes, Monday 8 p.m. South African time, Central African time, 8 p.m.
So then I think that's everything.
Great, wonderful. Thank you everybody for joining us. Thank you also for my co-panelists, for the educators, for their support, your support during the delivery of this webinar. Thank you very, very, very much. And yeah, we're definitely going to be keeping in contact, and you all have my email address now. And so let's definitely keep in contact. And I'm looking forward to going through those submissions and seeing the questions for the team in Antarctica. So thank you all very much. Cheer for the Springboks later. And let's hope we win this one as well. Great. Thank you, everybody.
Thanks, Judy. Thanks, team.
Yes.
Bye, guys.
Thank you, Judy.
Thanks. Bye, Samina.
Thank you, Judy. Bye-bye. Bye, Brittany.
Bye, guys.
Bye,
Thanks.
Judy. Okay. I don't like. Oh, okay.